Welcome, everybody, once again to another exciting presentation in the DeFord Lecture Series. As many of you, or most of you at this point, know, the DeFord Lecture Series has been a long-standing tradition in the Department of Geological Sciences here at the Jackson School, going all the way back to the 1940s. And it's been a venue for disseminating research both from members of the Jackson School community, long before there was a Jackson School, as well as distinguished scientists from around the world. It was named after Ronald DeFord a couple years ago. Ronald DeFord was a faculty member here in the department for starting in 1948, and he was a graduate advisor in the department from 1949 until 1967. He supervised a very large number of PhD students and master's students, but one of his large contributions was developing the lecture series as a means of scientific communication within the department. And so in his honor, we renamed it the DeFord Lecture Series a couple of years ago, and are very excited to have outstanding researchers from around the world joining us. Hopefully in the future, once again in person, but for the time being in this virtual setting. And today we're very excited to have Dr. Nandita Basu from Waterloo University joining us to tell us a little bit more about Dr. Basu and her research is Biana Cardenas, but handing over to you.
Thank you, John. I'm really pleased to be introducing today's speaker. So let me run you through all of Dr. Basu's amazing accomplishments, but let's start with her training. She got her bachelor's in civil engineering in Jadavpur University in Kolkata in India, and then did a master's at the IIT, Indian Institute of Technology in Kanpur, also in India, and then traveled across the world to Purdue University and received her PhD in 2006. Since then, she continued some amazing work on the topic she's going to talk about today too, and not surprisingly, she'd won a lot of accolades and honors for her contributions to our field. Most recently, she won the Saltzman Award for Excellence in Education and Mentoring from the Geosciences section of AGU. And she is a member of the Royal Society of Canada as well. And if you actually publish in hydrology, I hope you will have the pleasure of receiving an acceptance letter from her, because she is an editor-in-chief of the Journal of Hydrology. But if you don't, then I'm sure you can work it out and come up with a better paper that will get published in good journals like the Journal of Hydrology. So Professor Basu has actually been teaching in different places now. She started, I believe, at the University of Iowa, right? And then at her PhD alma mater at Purdue University, and eventually made it up north to the University of Waterloo. I might add something, Nandita, you might not know it. I think before there was Austin, there was a town here called Waterloo. So we are both in Waterloo. Anyway, so she's currently the director of the Collaborative Water Program at the University of Waterloo, there's a lot of water research in Waterloo, so that's a very big hat that she's wearing. And as you might know already, she's a professor and university research chair there. So Nandita, welcome. And I look forward to learning from you about water quality changes from small to extreme scales. So the floor is yours.
Thank you so much, Bayani, and thank you so much for inviting me to give this talk. I love the story about Waterloo. There's actually a Waterloo in Iowa too. Talk about Waterloos everywhere. Austin was actually one of the first places that I visited when I moved to Purdue to work with a professor there. And it holds a very dear place in my heart. I love the town when I visited a long time back. So today I wanted to talk to you about a lot of the research that goes in our group, specifically focusing on water quality challenges. And I'm really honored to be here virtually to give the talk. If you have any questions about anything, please feel free to drop me a note anytime. I had to share this. This is something a student of mine made, and he shared with me a few days ago, and I thought was really cool. So he was trying to capture the kinds of research that goes on in our group. I won't talk about all of these, but in a broad sense, our group is interested in questions where humans have changed the water system and impacted our water quality, be it forests and wildfire impacts on water quality and how it impacts water treatment, which is what Tyler studies, to a lot of our work in agricultural systems and agriculture and water quality, nutrient legacies. This is what I will focus a lot of my research, my talk today on, but we've also started working a bit on urban water systems. So wherever humans interact with water systems and it impacts our water quality, we are interested in our research in our group. Of course, the most fun part of the science is the people that do the science. So I wanted to start off by thanking the amazing group of people that I've had the pleasure to work with over the years. That's, I think, as an academic, that's the best part of an academic's career, the interactions with the students and seeing them light up when they figure things out. The question about water quality kind of thinking about this from the very, very large scale, thinking about sustainable development goals and how sustainable development goals are related to water quality. So if you think about it, if you think about goals of poverty reduction or food production, that's related to clean water, because if you want to produce more food, there will be more fertilizer application and water impact. So thinking about these sustainable development goals and how it relates to the specific goal of clean water and sanitation. If you think about the broad water quality challenge, we've made a tremendous progress in addressing water quality challenges. This is a paper that Peter Glick did a few years ago, where they looked at diarrheal deaths per 100,000 people. And we've made a huge amount of progress in terms of addressing water contamination. Of course, there are places all over the world that are still having water quality related challenges. Over 80% of the world's wastewater is discharged back into rivers without any treatment. Of course, that's not only a problem of the developing world, it's also a problem of the developed world. If you think about our First Nations communities, indigenous people, there's huge water challenges there. There's boiled water advisories. Most of them lack access to safe drinking water. Moving from water needs of human water needs to more water needs of the ecosystem. A lot of you might be familiar with this image where in the 1960s and 70s, rivers like the Cuyahoga River in Cleveland, Ohio, used to spontaneously catch on fire because there was so much pollutant in these rivers, which led to the Clean Water Act. And today the Cuyahoga is much cleaner, and there are these problems do not exist. I say this story because to make the point that a lot of our water quality problems, we have been successful in addressing some of them. One of the big problems, however, that still plagues us is the problem of harmful algal blooms. And these are different kinds of algal blooms that pollute our waterways, both our inland waters as well as our coastal water systems. And they are predominantly driven by excess nitrogen and phosphorus that we put on our fields, and they run off to our water bodies and lead to these large algal blooms. There's also questions about groundwater pollution. High groundwater nitrate concentrations. A lot of times groundwater nitrate concentrations, like you see on the map on the left, is above the drinking water limits of 10 milligrams per liter nitrate. And Texas is really red over there. That map shows how many drinking water violations has happened. The thing that's a little bit scary about groundwater and nitrate also is that the 10 milligram per liter limit that WHO set up, there are studies that are really addressing the fact that that's probably not the best limit, and there are impacts on health that people can see at a much lower groundwater nitrate concentrations. And indeed, this was highlighted in this recent, not so recent now, I guess, article that came out in New York Times, where they talked about the fact that nitrate in groundwater is rural America's own private flint. It's really polluted, and people that are reliant on private wells in rural areas around big cities don't have access to drinking water treatment. So a lot of times they are drinking water that are high in nitrate concentrations. When I was in Iowa, we did a survey with undergrads at the university where we were going around and talking to farmers and measuring nitrate in their groundwater. And it was an eye-opening thing for us because we were really shocked at the levels of groundwater nitrate concentrations we saw in that study. What I'm talking about now is what has been the focus of a lot of our research. So thinking about water quality problems, diagnosing these water quality problems using a lot of data. So in our lab group, we do a lot of data analysis and synthesis working with publicly available data sets. And I'll talk a lot about these diagnosis and modeling kind of work in the first part of my talk. But in the recent past, I've also gotten really motivated in the second box, which has been increasing in focus in our research group. So thinking about solutions, water quality solutions that address multiple sustainable development goals. I'll talk more about this also later in my talk. The thing about solutions that I find really intriguing is the question of scale. So if you think about solutions to water quality problems, a lot of the solutions are not technological or rigid solutions. They are solutions that we already know. We know how to do them, but there's questions about how do we scale up some of these solutions? How do we quantify what is the value of these solutions at large scales? And this is some of the work that our group has been motivated by doing. So coming back into the space of diagnosing water quality problem, I'm talking to a geoscience department. So I really wanted to bring about this idea of the role of the subsurface in addressing surface water pollution. And here I wanted to share a small story. So my PhD training was in groundwater contamination, modeling multi-phase fluid flow in groundwater systems. When I started working on questions about water quality problems that are more surface water problems, a lot of people asked me, why are you moving from groundwater to surface water? And the point that I wanted to make is that while manifestation of algal blooms, of course, it's a surface water manifestation, but it is a subsurface problem because most of the nutrients that come to your lake or your coastal area comes through the subsurface pathway. And it's really important to understand the role of that subsurface in addressing surface water pollution. And of course, this is not something that's new. Many years ago, Bob Farwell talked about it. A lot of work has been done in really understanding that surface water, groundwater connections and understanding the role of the surface water in groundwater as a groundwater in surface water challenges. However, at the macro scale, I would still argue that we really don't consider it as effectively as we should. So here's an article that came out a few years ago when there was this massive algal bloom in Lake Erie, one of the Great Lakes that the watershed that I live in drains into. And this article said climate change an aggravating factor, but runoff from agriculture seen as major culprit. And runoff, by definition, is the draining away of water from the surface area of a land. But a lot of that water, again, comes through the subsurface. Thus, non-point source pollution is a subsurface problem, but it's mostly studied by the surface water community. And I think that's one of the challenges in addressing the problem is that we don't understand and we don't effectively quantify the role of the subsurface in addressing this surface water challenge. And what that leads to is issues of disillusionment. So what do I mean by that? So here's an example of the Gulf of Mexico. The hypoxia in the Gulf of Mexico is really one of the biggest challenges that we are dealing with. Its dead zone was predicted to be the third largest in 32 years in 2017. At the same time, there has been huge amounts of efforts in addressing the problem. So for example, in 2008, the hypoxia task force was formed that said, well, let's reduce the size of the hypoxic zone to 5,000 kilometers square by 2015. 2015 came around, The size is 16,000 kilometers square in 2015, and now we have increased the goal to 2035. So why 2035? It's far enough away so we don't think about it. Similar stories everywhere you look. This is the Chesapeake Bay. Again, this idea that we put in a huge amount of money, invested a lot of resources, but water quality has not improved as fast as we thought it would. And again, this comes from the space. Talk to any groundwater hydrologist and they will tell you it will take tons, decades for you to see an effect of anything. However, this understanding has not really impacted our surface water policy making in a way that it should. This is moving across the country to Canada now. This is an article that came out, says 5-year fight removes less than 1% of phosphorus from the Lake Winnipeg Basin. Such lack of success generates skepticism. This is an example from the European Environmental Bureau that says time lags is a generic excuse to escape more stringent policy measures. So the main takeaway I want from this is that there are these landscape legacies that build up over decades of agricultural intensification. And what I mean by that is when you're applying fertilizer to the landscape, all of it is not taken up by crops. Some of it shows up in the stream, some of it might be denitrified, but a lot of it can build up in your landscape. And this is this legacy nitrogen or legacy phosphorus, which is captured in this blue shaded area. Thus, because you have these legacy sources in the landscape, when you make a difference, when you make a change to your land use practice, so let's say you've reduced fertilizer application, there will be a time lag for water quality improvement. And we really need to be able to quantify these time lags to be able to say how we can manage these systems better. So this kind of brings me to this outline of this talk, thinking about managing these legacies for water quality improvement, and broadly beyond legacies, how do we manage our landscapes that we live in, that we produce food in, so that we can sustainably grow food, but also improving our water quality. The first space in that roadmap is to think about quantifying legacies and lag times and adjust expectation. So a lot of our work in our lab focuses on this first bullet. So thinking about legacies and lag times and how we can quantify them better. In this space, the question that we ask is, how long will it take for the water quality to improve? So the idea is, if I make a change to the landscape, what is this lag time? And in order to answer this question in a really simplified way, there's two parts to this question. First is the part about stores. How much legacy is there? What form? Where? So for example, if you're thinking about nitrogen, you can have nitrogen dissolved in groundwater. This we call as groundwater legacy. You can also have nitrogen that's built up in soil organic matter, and that's biogeochemical legacy. You can also have nitrogen in reservoirs or in stream sediments, and that's network legacy. For any solute that you think about, have to think about where these stores are and can we quantify them better. And the next part is, how are they mobilized? And that's where a change in climate comes into play, because if you have a lot of legacy sources in the landscape, then an increasing precipitation pattern can mobilize those legacies faster. So to ask the question of how much legacy is there, we do in our group, we do a lot of mass balance studies, and we kind of look back for the last 100 years or so, reconstruct these mass balance data sets. And this is one of the, I would say in some ways, this is one of the most challenging parts of the study, because it's agricultural census has this information, but it is not easy to stitch together these data sets. So here's an example of such a data set. Here you look 100-year trajectory of phosphorus inputs in the Lake Erie Basin. And a couple things that I want to point out to you. One is that the black line that you see over here, that's the phosphorus surplus. So that's what I mean when I mean legacy phosphorus. This is the phosphorus, that's the difference between the input and outputs that's potentially in my landscape. So even if I reduce the fertilizer application, this phosphorus that's built up as legacy is going to keep bleeding into my water systems. The second thing that I want to point out to you is the fact that we have done better. Like if there is a peak in that phosphorus surplus and that has been decreasing, which means that we are getting more crop for the same amount of fertilizer that we put on the landscape. So there has been positive impacts. And the third thing that I want you to take away is the blue region in here. In this particular watershed, for example, manure is a big component of the input. And again, we have to think about these components and how we address these different components. So with that, we did similar work. So this is a data set that Danica Bryans and Kim Van Meter helped put together. This is from the 1930s to current, a nitrogen surplus, similar as the idea of phosphorus surplus, nitrogen surplus of the landscape. And this was done at the county scale, where we are kind of going back and quantifying these sources and sinks in the landscape to ask the question, how much is the potential buildup of nitrogen in the landscape? Coming at it from a very different angle, we in our group like to think about these questions from different angles. So here we are coming at it from the inputs and saying, what is the potential buildup? In this work, in this other paper, we looked at, well, let's take a look at soil cores all across and see how much has built up in the soil. So in this work that we did in 2016, we estimated using soil core data from field sites in Illinois and Iowa, as well as across the Mississippi River Basin. We were asking the question, how much nitrogen as soil organic nitrogen has built up in agricultural soils? And we found, without going into further details, that it was a significant amount. Agriculture normally applies about 100 to 150 kilograms per hectare per year. And we found that we were building up 50 kilograms per hectare per year in these landscapes. Since then, others have done in their catchment. So this is a study from France, where they also found estimate of nitrogen accumulation. And again, kind of coming back to this, we really need to be doing this more and more to constrain these budgets of how much legacy has accumulated. There's a really interesting study of urban systems where actually they found evidence that soil organic nitrogen and carbon was building up in urban soils, specifically in small residential areas. And this is also because of excessive application of lawn fertilizer that was building up nitrogen and phosphorus in these landscapes. Yet another study, this is a global scale study that looked at how much nitrogen is building up in the Vado zone in global aquifers. Again, there's uncertainties in these estimates, but we really need to quantify some of these numbers better. Now we ask the next question, of course, there is legacy buildup. So why does it matter, right? What does it mean in terms of water quality, which is the metric that we care about? So what you see in the image on the left is data from many, many watersheds across Europe, North America, and Asia. And what you see on the x-axis is nitrogen inputs. What you see on the y-axis is nitrogen load. So that's the stream nitrogen load. And each of the circle is one particular watershed, average values over multiple years for that watershed. And you see a linear relationship, of course, a scatter in the relationship. And in the mean, you see that nitrogen load is 27% of the net nitrogen inputs. And this is not new. Others before have used it. One of the things that's kind of hidden in this image is the time component. So when you look at this, you say, okay, so if I just go along the diagonal towards the origin, so if I decrease the net nitrogen inputs, my nitrogen loads should come down because this relationship holds. What we found is now if you take one of these circles and then expand it out in time, right? So then your axis is still the same, net nitrogen inputs and nitrogen load, but it is following the trajectory of one watershed in time. You see that as you increase the nitrogen inputs, your nitrogen loads increasing, but then as you're decreasing the nitrogen inputs, your nitrogen loads are not decreasing. And you have this really interesting hysteretic response, which happens due to these lag times in the landscape. And we really need to understand these hysteretic responses if we want want to manage for nitrogen pollution. And these hysteresis loops are different depending upon where you are. So here's an example of watersheds around US, and you see a lot of these anti-clockwise hysteresis loops. And right now what we are doing is looking at these loops and really trying to understand what controls these loop behaviors. These are examples of anti-clockwise loops. Here's an example of clockwise loops. Again, what controls these behaviors and what are the characteristics of these watersheds? So I'm going to jump ahead from that data-driven work to talk a little bit about models. So another way to think about it is, can we use models to predict how long will it take for water quality to improve? And in this case, we've done a whole bunch of models. We started out using some off-the-shelf models. So here is a modification of the SWOT model, where we modified it to, again, ask the question about lag time. The biggest challenge in thinking about modeling to estimate lag times is how to deal with a dynamic land use change. So a good example of that is to think about, let's say you are on a particular block of land, and let's say it's forested land. So if you want to put that in any watershed model like SWOT, it will say, well, it's forested land, so that means you will not have that much nitrate leaching from that land. But in reality, if that forested land was in cropland even 5 years before that, you will see very high nitrate concentrations. And we've actually gone out and measured a nitrate concentration in some forested areas, and they're really high, off the charts. And that's because this is converted forest from cropland. So you really need to think about a memory of a particular plot of land, and that memory impacts its nitrogen signature. So you have to track back in time. So when you're trying to work with this with a model like SWOT, you have to kind of consider a plot of land and how it transitions through various land use trajectories and how those transitions impacts its legacy dynamics. It was really complicated to do that in SWOT. So then we moved on to thinking about developing our own modeling framework to do this. It's a process-based modeling framework. We call it element exploration of long-term nutrient trajectories. There's carbon nitrogen cycling in the source zone. There's travel time distribution that route it through the landscape. It's similar in vein to a lot of process models. The thing that sets it apart is we do space-time substitution in a little bit of a different way. So instead of dividing a watershed into units of space, we divide the watershed into units of similar trajectories of land use. And then we model those different trajectories of land use through the system. And I can talk more about that if anyone is interested. And then we use this model to look at different watersheds. So here in this case, we're looking at the Mississippi Basin and the Susquehanna Basin. Both these watersheds were very unique in their land use trajectory. And we wanted to explore what that meant in terms of water quality impact. Overall, the model does a good job in predicting nitrogen load trajectories. The red diamonds are the modeled, and the gray area, red diamonds are the data, and the gray area is the model. What was really interesting in this study was this hump that we saw in our data. And our hypothesis was the reason we saw that hump is because during that time period, there was a massive land use conversion that happened across the Mississippi River Basin. You had a massive conversion of prairie grassland to row crop to cropland, and that led to oxidization of organic matter and this big pulse. What was really interesting is we looked at some sediment core data that was there from the Gulf of Mexico, and we found that our hump did correspond to a hump in the pigment data that showed that there was truth to the fact that there was more productivity there. Models like this are valuable because they then allow us to say that if you want a 60% reduction in nitrogen, how long will it take for you to achieve that? And in this case, we found that it will take 35 years to achieve that goal. It's important to keep that in mind, however, that in this case, we are talking about only things that's reducing the nitrogen inputs at the farm field. There are also ways of improving water quality by more downstream measures like wetlands. And later I will talk about that. And that might make the process much faster. Oops. Okay, so I'm not going to go too much, but we've also developed a similar model for phosphorus. Phosphorus is a little bit more complicated in some ways because of thinking about erosion and other processes. Models like this are really helpful because they tell you where the phosphorus is hiding. So in this case, we found that a lot of the phosphorus was tied up in the soils in the Lake Erie Basin. And they also allow us to say things like, what are the management practices that would have the most impact? And in this case, we found because a lot of the phosphorus was tied up in legacy phosphorus, one of the biggest knobs to turn would be manure handling. So really focusing on the manure problem would lead to the fastest improvements in water quality. So jumping into the next part, which is thinking about this question, if legacy is indeed such a big problem, so you're having these build up in our landscape, can we think about legacy as a resource? This is not work we have done, but it is really interesting to think about other studies that have come up. So this is a study in global change biology, where they found using isotopes that less than half of the nitrogen that is taken up by crop is today's fertilizer. It is past fertilizer that the crops pick up. Other studies that have looked at if you reduce fertilizer applications, these studies show that your crop yields don't change, but your water quality improves. So there's potential, again, thinking about solutions, there's potential of improving water quality without giving up on crop productivity. What is required, of course, is large scale, figuring out ways using emerging technologies to be able to apply less fertilizer. And of course, this is more a social and political problem, thinking about ways to incentivize farmers to apply less fertilizer. And this has both water quality impact, but also a climate impact, because if you apply less fertilizer, nitrous oxide from fertilizer is a greenhouse gas emission. So again, thinking about climate and water together in terms of these solutions. The other key piece in thinking about water quality solution is we really have to be getting to spatially targeted measures when we think about various solutions. Most of the practices that we do today in North America are random. So farmers are randomly sign on to different conservation practices. And if you want to be more intensive in efficient in our abilities to improve water quality, we have to get at more spatially targeted measures. So here's a small example of something along this line that we are working on with some of the manure work. So what you see in this image, the green areas are areas in US where manure is in deficit, so crops need more fertilizer, and the purple areas are areas which is more livestock dominated, so there's more excess of manure. And one of the big reasons this happens is, of course, agricultural intensification. So once upon a time, our landscapes looked more like this, where there was some animals and you would use the manure for crop. But now our agricultural operations look more like this. So there is agricultural intensification, and you get a lot of manure in areas that you don't really need it for crop growth, which leads to poor water quality. So this study shows that as you increase manure, your nitrogen use efficiency, so the amount of nitrogen that is effectively harvested in crops, decreases, and you get poorer and poorer water quality. A big way that we can use manure is, of course, through use in biogas plants. So manure can be used through biogas, and this is really interesting because, of course, you can get money out of it. You can have environmental benefits out of it because manure has reduced greenhouse gas emissions and improved water quality. But what's missing? And one of the things that our group is focusing on is, can we develop simple ways to think about spatial optimization methods to say, how can we site these biogas reactors so that we get the most water quality benefits, greenhouse gas benefits, and it's economically viable. So this is a pilot study that we did using US scale data sets, not published yet, but we had just launched into a project with a colleague in energy policy and transitions in energy policy, where we are asking this question: how do we take something like manure to biogas and scale it up at a macro scale and really consider the trade-offs, both from a water quality as well as a greenhouse gas emission perspectives? I'm not going to go into the fourth piece. The other piece in terms of thinking about water quality is really we need to get better at monitoring. We really need to get better at saying when we are putting different measures in the landscape, what are the benefits of that? The last piece I will talk about in the last 15 minutes or so is this idea of coupling short-term and long-term measures, specifically focusing on one of the research in our group. What do I mean by short-term and long-term measures? So if you think about this question of legacies, right? Part of our challenge when we're thinking about it is if you say, well, 96% of the phosphorus that I'm applying to the landscape is building up as legacy in my soils. So what does it matter what I do now? It'll take decades for that to have an effect. And what that means is there is only so much you can do by focusing on fertilizer management, or what we call typically as long-term measures, because it will take a long term for the water quality to benefit. You also need to think about more downstream measures. So these are wetlands, riparian buffers, downstream measure that treat the pollutant once it has once the horse has left the barn. So the groundwater nitrate that has left your farmer's field has to be treated more downstream if you want a water quality benefit. So one of the kind of water quality measures that's used most often is wetlands. Wetlands, we know, retain excess nutrients and improve water quality. The question that we're kind of motivated by is for asking is what is the potential of wetlands across a large scale for water quality improvement? And in this case, some of the motivation of our work comes from work done by Bayani and others, where they looked at denitrification in the Mississippi River network and figured out where the hotspots of nitrogen removal are. I think we really need to be doing more and more work like this, where we are looking at these large scales, and even if we are doing really, really simplified models, being able to say what the potential of these systems are in terms of improving water quality. There's also been some work related to riparian corridors, more engineered measures like two-stage ditches. Part of the challenge in all of these work is thinking about the role of these measures in improving water quality. What do you mean by that? This kind of triggered with me with a conversation that I was having with a colleague one time, and I was talking to him about riparian areas, and he asked me the question, so how much nitrogen do riparian areas remove anyway? And I realized when he asked me this question, it's really, in some ways, a really simple question, but in some ways, my take was, I don't know. I don't know the answer to that question. So that's kind of the motivation of this work, is how much do current wetlands, how much nitrogen do they remove across continental US? So this work started with some work in 2017 with a grad student in my group, Fred. And in this case, we were asking, what is the role of wetland size in nutrient removal, and what is the potential for nutrient retention in wetlandscapes? So to answer this question, we started with a large-scale meta-analysis where we looked at, Fred combed through hundreds of papers and found wetlands and reservoirs and lakes all across the world, and got data of nitrogen inputs and outputs from each of these systems. And we put all those together. I'm not going to go into a lot of the details, couple that with a simpler model. And we estimated the first order removal rate constant in these systems. And one of the things that we found is that smaller wetlands have faster denitrification kinetics. And this is similar to headwater streams that are known to be more reactive. And I can go into more details about that if anybody is interested. But then we wanted to scale that up and ask the question, how much nitrogen is removed by wetlands across the continental US? And given that we are missing in-person conferences a lot, this idea for this project kind of came together. If anybody recognizes that San Francisco, one of my favorite cafes in San Francisco, where we were sitting and talking about this, because it kind of brought two parts of my research together. One that was focused on more wetlands, and the other was more in this world of nitrogen inputs and outputs. And we wanted to bring these two pieces together. So the way we went about it is we took the first order reaction rate constant, the K value that Fred got from his meta-analysis. And in this case, he developed an empirical relationship that related that K value to the size of the wetland. And in this case, we use surface area as a surrogate for residence time, which of course has its limitation, but at the large scale, that was the only data that we had. And then we use the National Wetland Inventory data set, which has spatial data for 30 million wetlands. So we did that. And so at the end of the day, we could say for each of these wetlands, we estimated this fractional nitrogen removal based on its size and its residence time. And that's what you see in here. So this is the % nitrogen removal potential of wetlands in watersheds across the continental US. Of course, that map looks really, really simple, similar to the wetland density maps, because of course, when there is more wetlands, you get more potential nitrogen removal. But that's still potential. Now we ask the question, well, how much nitrogen is removed in fact? So in order to answer this question, we linked nitrogen sinks with sources. So here we went into the work that I talked about before, where we have developed this long-term nitrogen input data set. And we estimated the mass removed as the fractional removal times a factor times the nitrogen surplus in this landscape. And at the end of the day, we estimated that nitrogen, that 0.86 teragram of nitrogen was being removed by wetlands across US. What does that mean? That means that without existing wetlands, nitrogen loads in the Mississippi River Basin would be 50% greater than it's now. Of course, there's a huge error bound around that 50%, but that tells us that it is a significant amount, and that as there is fear of loss of wetland protection with different Clean Water Act rules and significant nexus issues, we really should think about this number and how it impacts us. The other thing that was really enlightening to us by doing the analysis is that the disconnect between sources and sinks. So on the left hand, the top image is the wetland density, and the bottom image is where the nitrogen excess is. So what we are seeing over here is, if you look at the XY image, where you have most of the wetlands is not where nitrogen is, and where you have more nitrogen, that's not where the wetland is. So there's a spatial decoupling of nitrogen sources from wetland dense region, which really impacts our ability to remove nitrogen from these systems. So then we ask the question, how can wetland restoration be used for improvements in water quality? In order to answer this question, we simulated different realizations of wetland restoration. We said, well, let's say we are going to increase wetland by 10%. Let's say we are going to do it randomly across the landscape. Let's say we are going to have no agricultural land loss. And then finally, our favorite scenario, targeted wetland restoration in agricultural areas in Mississippi Basin, in California, where we have the highest end surpluses in the landscape. For each of these scenarios, we estimated the nitrogen removal. And the main thing that I want you to take away from here is this graph on the right. So what we found is that with the 10% nitrogen removal, a 10% increase in wetland area, a targeted restoration can reduce 40 times more nitrogen than a non-targeted restoration. Of course, it's more expensive. A targeted restoration is definitely more expensive because land values in the Mississippi Basin agricultural area is greater, but it's only double the cost of non-targeted restoration. And the costs we found, though they are high, are in line with some of the spendings across US for various conservation measures. So the point that I want to make is that the costs are not exorbitant. We need to target some of these expenses better. We need more targeted strategies if we want water quality improvement. So to summarize this work, what we found that a targeted 22% increase in wetland area in the Mississippi River Basin could result in a 40% decrease in nitrogen load, bringing us closer to some of the policy goals. The thing that's also important to remember in that space is wetlands also sequester carbon and provide other ecosystem services. So when you're thinking about climate solutions and natural climate solutions, there are also other synergies with wetland restoration. And this is just one example, right? So if you think about any of these solutions, whether it's lowering fertilizer application, whether it's investing money in riparian restoration, what is important to do is to really quantify how much benefits they have at the large scale for us to make a case for these strategies for a water quality improvement. So to summarize, kind of bringing you back to this space is thinking about spinning the problem from thinking about it as a problem to legacy as a resource, and thinking about the question from different angles to think about solutions at large scales. With that, thank you for your time, and I'd love some questions.
All right, well, I'd like to thank you once again for a really very interesting talk. And I definitely think that there's a lot of potential here for taking this sort of research and then combining it with economic analysis to come up with policy solutions. So a lot of fruitful ground here for future work. But thank you very much. Thank you everybody for joining us today. And I look forward to seeing everybody, or not seeing you as the case may be, a week from now, next Thursday. And with that, the DeFord lecture is adjourned, but you're welcome to stay on and have a few words with Bayani and Nandita if you wish.
And thank you all for the invite. Really, really appreciate it. And if anybody has any questions, feel free to reach out to me. If anybody wants to do graduate studies or looking for postdoc, feel free to reach out to me. There's quite a few opportunities in the group, and we'd love to
send along those opportunities. We'll email it out, Nandita. But thanks again. Thank you very much. That was great.